In this exercise, we find two cubic spline functions that pass through the points 1, 0, 2 ln 2, 3 ln 3, and 4 ln 4. We will be looking for two cubic splines. The first one is a natural cubic spline through the 4 points. The second one is a clamped cubic spline through the 4 points where the slopes at the endpoints are specified. For this exercise, we will use the following form for each of the polynomial segments. P sub k of x is equal to a sub k times the cube of the quantity x minus x sub k plus b sub k times the square of the quantity x minus x sub k plus c sub k times the quantity x minus x sub k plus d sub k. K here goes from 0 through n minus 1. We determine the value of n through the indexing of the points. We designate the first point 1, 0 to be x sub 0, y sub 0, and so we start our indexing at k equals 0. 2 ln 2 is x sub 1, y sub 1. 3 ln 3 is x sub 2, y sub 2. And the last point, 4 ln 4, is x sub 3, y sub 3. And so n is equal to 3. For this exercise, we will be solving for a sub k, b sub k, c sub k, d sub k directly. We will not use the values of the second derivatives at the different points or different nodes as the unknowns. There is another method that uses precisely the second derivative values as the unknowns, but we will not employ that method here. To come up with a cubic spline for each case, we come up with a system of equations. Both cases share a common core of equations. So we proceed by finding that common core of equations. The first group of equations that we look for are what we refer to as the node equations. To get the node equations, we plug in each x sub k into the polynomial segment p sub k. Then we match p sub k of x sub k to y sub k. This is to guarantee that the cubic spline passes through the different points. The first 3 terms cancel because we have x sub k minus x sub k, and the only term left will be d sub k. And so d sub k equals p sub k of x sub k, and of course this corresponds to the y sub k value. And so for the first set of node equations, we have d sub 0 equals y sub 0, which is equal to 0. D sub 1 equals y sub 1, which is equal to ln 2. And d sub 2 equals y sub 2, which is equal to ln 3. Now x sub n, y sub n is the only point that is only a right endpoint. That is, if we have arranged the x sub k's as a strictly increasing sequence. We plug in x sub n into p sub n minus 1, which is the last polynomial segment. And so p sub n minus 1 of x sub n is equal to y sub n. With n equaling 3, x sub n y sub n is equal to x sub 3 y sub 3. P sub n minus 1 should be p sub 2, and so we're looking at p sub 2 of x sub 3 or p sub 2 of 4. X sub 2 is equal to 3. And so we have the following equation. A sub 2 times the cube of the quantity 4 minus 3 plus b sub 2 times the square of the quantity 4 minus 3 plus C sub 2 times the quantity 4 minus 3 plus D sub 2 is equal to ln 4. The next group of equations that we look for is what we refer to as the continuity equations. This just means that the different polynomial segments or consecutive polynomial segments meet at shared nodes. For example, the polynomial segments p sub k and p sub k plus 1 share the common node at x sub k plus 1. Continuity dictates that p sub k of x sub k plus 1 equals p sub k plus 1 of x sub k plus 1. The first pair of consecutive polynomial segments is made up of p sub 0 and p sub 1. The left endpoint for p sub 0 is at x sub 0 equals 1, while the shared node is at x sub 1 equals 2. And so we have the left side of the first continuity equation. The right side is p sub 1 of x sub 1, and p sub 1 of x sub 1 is y sub 1, and y sub 1 is d sub 1. And so we have the right side of the first continuity equation. The next pair of consecutive polynomial segments is made up of p sub 1 and p sub 2. We simply modify this equation by increasing all of the indices by 1. The new nodes are now at x sub 1 equals 2 and x sub 2 equals 3. The next set of equations that we derive are the first derivative equations at the shared nodes. The general equation is p sub k prime at x sub k plus 1 equals p sub k plus 1 prime at x sub k plus 1 for k equals 0 through n minus 2. So we will need p sub k prime. Differentiating p sub k of x, p sub k prime of x is equal to 3 times a sub k times the square of x minus x sub k plus 2b sub k times x minus x sub k plus c sub k. One thing we note is that when x is replaced by x sub k, we have p sub k prime of x sub k equals c sub k. This time, we can use the continuity equations as a template for the left side of the first derivative equations. We merely have to change the coefficients, retain the c sub k terms, leave out the d sub k terms, and decrease the exponents by 1. For the right side of these equations, which is p sub k plus 1 prime of x sub k plus 1, we just have c sub k plus 1. The last set of equations that is part of the core set of equations for the two types of cubic splines that we are looking for are the second derivative equations. These are also very similar to the continuity equations and the first derivative equations. This time we're looking at p sub k double prime. We're looking at p sub k double prime at x sub k plus 1 and p sub k plus 1 double prime at x sub k plus 1. P sub k double prime is 6 times a sub k times the quantity x minus x sub k plus 2b sub k. For the left side of the second derivative equations, we use the first derivative equations as the template. We simply change the coefficients, decrease the exponents by 1, leave out the c sub k terms, and retain the same x values. To get the right side of these equations, we first note that p sub k double prime of x sub k is simply the term 2b sub k, so that p sub k plus 1 double prime of x sub k plus 1 is equal to 2b sub k plus 1. These are the core equations for our cubic spline curves. There are 10 equations total, but we have 12 unknowns, since we have 3 polynomials, p sub 0, p sub 1, and p sub 2, and each one of them has 4 unknowns. So we are missing 2 equations. The 2 missing equations are supplied by the type of cubic spline that we are looking for. The first type of cubic spline that we are looking for is what is called a natural spline. A natural spline has the second derivative values at the leftmost endpoint and the rightmost endpoint both at 0. And so p sub 0 double prime of x sub 0 equals 0, and p sub n minus 1 double prime of x sub n equals 0. At the left endpoint, when the index is equal to 0, we have p sub 0 double prime of x sub 0 equals 2b sub 0, and so 2b sub 0 is equal to 0. At the right endpoint, n minus 1 would be equal to 3 minus 1 or 2, and so we are looking at p sub 2 double prime of x sub 3. X sub 3 is equal to 4, and x sub 2 is equal to 3. And so the second equation is 6a sub 2 times the quantity 4 minus 3 plus 2b sub 2 equals 0. We now have a complete set of system of equations, and we can solve for the different unknowns. Using a computer software to find the different values of the unknowns, this is the solution that we obtain. And here are the formulations for the different polynomial segments. And here is the graph of the cubic spline, where we have colored the different segments differently. This first blue segment is p sub 0, this is p sub 1, and this is p sub 2. The green curve is the graph of y equals ln x, which we might have surmised as the original function from which the different nodes came. Now we look for the clamp spline. For the clamp spline, the slopes at the left endpoint and the right endpoint are prescribed. At the leftmost endpoint, we prescribe the slope sub 0. And so p sub 0 prime of x sub 0 should be equal to slope sub 0. At the rightmost endpoint, we prescribe the slope sub n. And so p sub n minus 1 prime of x sub n equals slope sub n. Recall that p sub k prime of x sub k equals c sub k. And so p sub 0 prime of x sub 0 equals c sub 0. Therefore, c sub 0 should equal the prescribed slope of minus 10 for the leftmost endpoint. For p sub n minus 1 prime of x sub n, we are looking at p sub 2 prime of x sub 3. Using this equation in the first derivative equations as a template, with the index at 2, x sub 3 equals 4, and x sub 2 equals 3, we get 3a sub 2 times the square of the quantity 4 minus 3, plus 2b sub 2 times the quantity 4 minus 3, plus c sub 2, and this should equal the prescribed slope sub n. Slope sub n is given to be minus 20. And so we have another complete set of equations. We solve for the unknowns using a computer software, and these are the values that we obtained for the different unknowns. And here are the formulations for the different polynomial segments. Here is the graph of the cubic spline curve along with the natural logarithm curve. We can see the obvious discrepancy between the cubic spline curve and the natural logarithm curve. This is largely due to the fact that the slope of the logarithm curve at the left endpoint is not equal to minus 10 as we had prescribed for the Clamp spline. It is equal to 1. At the right endpoint, the natural logarithm curve has a slope of 1/4, not minus 20.